Hi, I'm Hai Wu, presenting the virtual sparse convolution for multimodal 3D object detection. This is done by Hai Wu, Qingluo Wen, Xiaohui Shi, Xin Li, and Cheng Wang. In this work, we focus on 3D object detection, which has wide applications in the field of safety monitoring and self-driving. The 3D object detection is the key technology to perceive the dynamic objects. The 3D object detection task is generally defined as, given a set of point clouds or images, find out the bounding box of all objects. Each box defined by XYZ coordinates, width, length, height and azimuth angle. The RGB image and LiDAR data can complement each other and usually boost 3D detection performance. But, based our statistics, only 5% to 10% pixel has a explicitly correspondence with LiDAR points. The remain pixels without depth are difficult to be fused with LiDAR points. Recent SFD converted the image data into virtual points based on depth completion, showing promising 3D detection performance. However, the virtual points are generally very dense and noisy. Here we show a sample from Kitty dataset. The virtual points are much dense than regular LiDAR points, so the inference speed of 3D detection is significantly decreased. Besides, the noises brought by inaccurate depth completion exist in the virtual points. Since it is very difficult to distinguish the noises from the background in 3D space, the localization precision of 3D detection is greatly degraded. To address these two problems, we proposed a new operator, virtual sparse convolution, called VirConv, for better 3D detection. The VirConv contains two key designs. A stochastic voxel discard method to alleviate the density problem. A noise-resistant submanifold convolution layer to address the noise problem. Built upon VirConv, we present three new multimodal detectors, a VirConv L, a VirConv T, and a semi-supervised VirConv S for efficient, high-precision, and semi-supervised 3D detection, respectively. To better understand our detector, we first introduce the VirConv L detection framework. Our detector takes the LiDAR points and virtual points as input. Then the points are converted into voxels, which are put into a backbone network, called VirConvNet for features encoding. After that, the encoded features are used for proposal generation and refinement by a detection head. Finally, our detector output a set of 3D bounding box of objects. Our contribution mostly lies in the design of VirConvNet, which consists of 4 VirConv blocks with 8 times down sampling strides. Each VirConv block contains 3 basic layers, including STVD layer, 3D SPConv layer and NRConv layer. The STVD layer is our newly designed stochastic voxel discard layer for solving the density problem, and the NRConv layer is the newly designed noise-resistant submanifold convolution for solving the noise problem. We first discuss the density problem in detail. Based on our statistics on the Kitty data set, the number of virtual points are 27 times than regular LiDAR points. As a result, the detection speed is slower 2 to 3 times than LiDAR-only detector. However, based on our observation, geometries of nearby objects are often relatively complete in LiDAR scans. Hence, most virtual points of nearby objects only bring marginal performance but increase the computational cost significantly. Therefore, we design an STVD, stochastic voxel discard, scheme, which alleviates the computation problem by discarding nearby redundant voxels. We called input STVD. A simple method is to downsample the point clouds using FPS, but is much time-consuming. The random sampling is fast but lows much shape queue of distant object. We proposed the bin-based sampling, which randomly discard voxel based on different distance, can achieve better trade-off between efficiency and accuracy. In addition, the points of the distant object are much sparser than the nearby objects. The STVD can simulate sparser training samples to improve detection robustness. We called layer STVD. We then discuss the noise problem in detail. Based on the sample from the Kitty data set, the inaccurate depth completion brings large amount noise points. As a result, the detection performance is lower 9% than LiDAR-only detector in the terms of AP. We observed that noise is mainly distributed on the instance boundaries and can be more easily recognized in 2D images. Our idea is to extend the receptive field of sparse convolution to the 2D image space, and distinguish the noise without the loss of shape cues. Specifically, given n input voxels formulated by a 3D indices vector and a features vector, we first encode the geometry features by the 3D submanifold convolution kernel. Since the noise is mostly distributed on the 2D instance boundaries, we extend the convolution receptive field to the 2D image space and encode the noise-aware features using the 2D neighbor voxels. Specifically, we first convert the 3D indices to a set of grid points based on the voxelization parameters. Since state-of-the-art detectors also adopt the transformation augmentations, we transform the grid points backward into the original coordinate system. Then we project the grid points into the 2D image plane based on the LiDAR camera calibration parameters. After the 3D and 2D features encoding, we adopt a simple concatenation to implicitly learn a noise-resistant feature, which are used for downstream 3D detection. We then construct a high-precision VirConv based on our VirConv. We fuse the multi-stage and multi-transformation method into a single pipeline, and extract the LiDAR features and images using VoxelNet and VirConvNet, respectively. We last extend the VirConv to a high-performance semi-supervised detector based on the pseudo-label framework. We first pre-trained the VirConv using labeled data, then using this detector to generate pseudo-labels on large-scale unlabeled data. And last we fine-tune the VirConv using both labeled and unlabeled data. We conducted experiments on the widely used Kitty 3D Vision benchmark to validate the effectiveness of our method. Our method ranks first on 4 benchmarks. Our VirConv ranks first on the 3D car detection leaderboard. Our VirConv also ranks first on the BEV car detection leaderboard. Our VirConv also ranks first on the 2D car detection leaderboard. We then conducted a series of experiments on the Kitty validation set to select the best hyperparameters. We also conducted many experiments to test the effectiveness of each proposed component. The experimental results show that every component play a key role to the final performance improvement. We last show a visualization results to better understand how our method improve 3D detection. Thanks for your attention.